Every probe we have ever launched, every astronaut who has ever flown, every satellite that has ever orbited any planet has done so within the heliosphere. We have never operated anything outside this bubble except the 2 Voyagers, and those 2 spacecraft are the only instruments we have ever placed in that environment. When their power runs out, as it will within the next several years, we will have no presence in interstellar space at all. We will be entirely contained within the heliosphere, shielded, protected, and utterly ignorant of the conditions outside unless we build something new and send it out again. The heliosphere has been protecting this solar system for roughly 4.5 billion years. Every evolutionary step that led to complex life on Earth occurred within its shelter. Every species that has ever existed, every ecosystem that has ever functioned, every molecule of DNA that has ever replicated on this planet did so under the reduced cosmic ray flux that the heliosphere provides. We evolved inside the bubble, and until Voyager, we had no direct evidence of what conditions are like outside it. Now we do. And the measurements make clear that the heliosphere is not merely a feature of the solar system, it is the feature. The one structure that separates the relatively benign interior of our stellar neighborhood from the full, unfiltered severity of galactic space. A structure that is not permanent, not fixed, and not guaranteed to remain the size it is today. What Voyager measured when it crossed that boundary, instrument by instrument and particle by particle, changes everything. The numbers are precise, the implications are unsettling, and together, they describe an environment that is far more hostile than the serene darkness most people imagine when they picture the space between stars. The moment Voyager 1 crossed the heliopause, every instrument still functioning aboard the spacecraft began telling the same story from a different angle. The particle detectors saw it, the magnetometers saw it, the plasma wave receiver saw it. Each sensor registered a distinct change in its own domain of measurement, and when those individual changes were assembled into a single coherent picture, they described an environment that no one had ever directly sampled. Not inferred from the absorption patterns of distant starlight, not modelled in a computer simulation, not estimated from theoretical equations, measured, counted, recorded, transmitted back to Earth as ones and zeros embedded in a radio signal weaker than the glow of a birthday candle seen from the distance of the moon. The data arrived slowly, at a rate of roughly 160 bits per second, the speed of a telegraph compared to modern broadband. But every bit mattered. Every number represented a direct encounter between a 1970s-era sensor and the actual material that fills the space between stars. And the numbers were not what most people would have expected. Start with the particles. Voyager 1 carries 2 instruments capable of detecting energetic charged particles. The Cosmic Ray Subsystem, or CRS, measures higher energy particles, those with energies above roughly 1 million electron volts. The Low Energy Charged Particle Instrument, or LECP, covers a broader range including lower energy ions and electrons. Together, these 2 instruments function as a particle census, counting how many charged particles of various types and energies pass through the spacecraft's vicinity during any given time interval. Inside the heliosphere, both instruments had spent decades recording a population dominated by particles of solar origin. The solar wind itself consists of relatively low-energy protons and electrons, but the termination shock and heliosheath produce higher-energy particles called anomalous cosmic rays. These are atoms from the interstellar medium that drifted into the heliosphere as neutral particles, became ionized by solar ultraviolet radiation, were picked up by the solar wind's magnetic field, and then accelerated to high energies at the termination shock. They are interstellar in origin but solar in their acceleration. They carry a distinctive energy signature that marks them as products of the heliosphere's internal physics. When Voyager 1 crossed the heliopause, the anomalous cosmic ray population vanished. Not gradually, not partially. It dropped to near zero within a matter of days. This was one of the sharpest transitions in the entire crossing dataset. The anomalous cosmic rays exist only inside the heliosphere because they require the termination shock to reach their observed energies. Outside the heliopause, the termination shock is behind you. The acceleration mechanism is gone. The particles simply are not there. Replacing them was the unmoderated population of galactic cosmic rays, arriving at intensities the spacecraft had never experienced. These particles originate from sources scattered throughout the Milky Way, primarily supernova remnants, but also pulsars, binary systems, and other energetic phenomena. They have been bouncing through the galaxy's tangled magnetic field for timescales that can reach millions of years. By the time they arrive at any given location in interstellar space, their directional information has been almost entirely scrambled. They come from everywhere at once. An isotropic rain of high-energy particles with no preferred direction and no pause. Voyager 1's CRS instrument recorded the galactic cosmic ray intensity climbing to a level roughly 2 to 3 times higher than the maximum values observed inside the heliosphere during the deepest solar minimum conditions. This is the baseline. This is what interstellar space delivers continuously. Regardless of solar activity, regardless of the 11-year cycle, regardless of anything the Sun does, the heliosphere had been suppressing this flux by the substantial margins described earlier. Outside the bubble, the full galactic value arrived without apology. But the increase was not uniform across all energies. For cosmic rays in the lower energy range, below roughly 200 million electron volts per nucleon, the increase was far more dramatic. These are the particles most effectively blocked by the heliosphere's magnetic shielding. Inside the heliosphere, even during solar minimum, the flux of these lower energy galactic cosmic rays is suppressed by factors of 5 to 10 compared to interstellar values. Once Voyager crossed the heliopause, these particles appeared in abundance for the first time. The instrument registered flux levels that had never been seen during the spacecraft's entire 35-year journey through the heliosphere. This low-energy cosmic ray population matters because it represents the component most efficiently absorbed by matter. When a lower-energy cosmic ray proton strikes a material surface or passes through a spacecraft hull, it deposits its energy over a shorter distance than a higher-energy particle would. The ionization density along its track is higher. The damage per unit path length is greater. For biological tissue, lower-energy cosmic rays contribute disproportionately to radiation dose precisely because they are more readily absorbed. The heliosphere's ability to exclude these particles is one of its most important protective functions. Without that exclusion, the radiation environment changes not just quantitatively, but qualitatively. The character of the radiation shifts toward a regime that is more biologically damaging per particle. The particle data also revealed something subtle but important about the transition itself. The changeover between solar-dominated and galactic-dominated particle populations did not happen with perfect simultaneity across all energy ranges. Higher energy galactic cosmic rays, which penetrate the heliosphere more easily, showed a more gradual transition. They had already been partially present inside the outer heliosheath. Lower energy particles, which are more effectively excluded by the heliosphere, showed a sharper step at the boundary. And the anomalous cosmic rays, which exist only within the heliosphere, dropped off precipitously. This energy-dependent transition profile provided independent confirmation that the heliopause is a real physical boundary, where the shielding mechanism changes, not merely a gradual thinning of solar influence. Now turn to the magnetic field. Voyager 1 carries a magnetometer, one of the most essential instruments aboard, mounted on a long boom, extending away from the spacecraft body to minimize interference from the vehicle's own magnetic signature. This instrument measures the strength and direction of the ambient magnetic field with sensitivity sufficient to detect fields of a fraction of a nanotesla. Inside the heliosphere, The magnetic field is solar in origin. It follows the Parker spiral geometry, wound into a pattern determined by the sun's rotation and the outward flow of the solar wind. The field strength at Voyager's pre-crossing location in the outer heliosheath measured roughly 0.1 to 0.2 nanotesla. The direction was consistent with the expected solar field orientation at that distance and latitude above the solar equatorial plane. After the crossing, the magnetic field did not disappear. This was itself a finding worth noting. Some early conceptions of the heliopause imagined a transition from a magnetized interior to a relatively unmagnetized exterior. The reality proved entirely different. The interstellar medium carries its own magnetic field, generated and sustained by currents flowing through the galactic plasma, compressed and shaped by shockwaves from supernovae, sculpted by the motion of stars and gas clouds through the galaxy over millions of years. This galactic magnetic field has a typical strength in the solar neighborhood of roughly 0.3 to 0.5 nanotesla, actually somewhat stronger than the exhausted solar field in the outer heliosheath. Voyager 1 measured this transition directly. The field strength increased modestly across the heliopause boundary, from roughly 0.2 nanotesla inside to roughly 0.4 to 0.5 nanotesla outside. More importantly, the field direction changed. The interstellar magnetic field in our local galactic environment runs at an angle significantly different from the solar equatorial field that dominates inside the heliosphere. Voyager's magnetometer tracked this directional shift, recording a rotation in the field vector that confirmed the spacecraft had entered a magnetically distinct domain. However, the directional transition was not as clean as many models had predicted. Theoretical work prior to the crossing had suggested that the heliopause should produce a sharp, well-defined rotation in the magnetic field direction, a clear pivot from solar to interstellar orientation. Instead, the data showed a more gradual rotation occurring over days to weeks. The field direction shifted progressively rather than flipping abruptly. This indicated that the heliopause is not a mathematical surface of zero thickness, but a finite transition layer where solar and interstellar magnetic fields intermingle. Material from both sides of the boundary coexists in this layer, creating a region of mixed magnetic character that the spacecraft traversed over a period that corresponded to a physical distance of roughly a fraction of an astronomical unit. This finding had implications for how the heliopause functions as a barrier. A sharp boundary would act more like a wall, cleanly separating interior from exterior. A gradual boundary behaves more like a membrane, allowing some mixing and exchange of material between the two regions. The magnetic data suggested that the heliopause permits limited interchange of particles and field between the heliosphere and the interstellar medium, particularly in the boundary layer itself. This partial permeability had been suspected from theoretical models, but never confirmed by direct measurement until Voyager provided the evidence. The magnetic field data also revealed ongoing variability in the interstellar medium. After crossing the heliopause, Voyager 1 did not enter a perfectly static magnetic environment. The field showed fluctuations in both strength and direction on timescales of hours to days. These fluctuations reflect turbulence in the interstellar plasma, driven by processes operating on scales much larger than the spacecraft could sample directly. The interstellar medium is not calm. It is dynamically active, stirred by shock waves from distant supernovae, by the relative motion of interstellar clouds, and by magnetohydrodynamic instabilities inherent to any conducting fluid threaded by magnetic fields. This turbulence matters because it affects how cosmic rays propagate through interstellar space. Galactic cosmic rays scatter off magnetic irregularities as they travel through the medium. The scattering rate depends on the turbulence spectrum, the distribution of magnetic fluctuations across different spatial scales. Voyager's measurements of interstellar magnetic turbulence provided the first direct constraints on this spectrum in the very local interstellar medium, data that feeds directly into models of cosmic ray transport throughout the galaxy. Voyager 2's crossing in 2018 added a dimension that its twin could not provide. As noted earlier, Voyager 2 retained something its twin had lost decades before: a functioning plasma science instrument capable of directly measuring the speed, density, temperature, and flow direction of charged particles. Where Voyager 1 had been forced to infer plasma properties indirectly through oscillation frequencies, Voyager 2 could sample the interstellar plasma with the precision of a laboratory instrument pressed against the medium itself. The difference in data quality was transformative. At the heliopause crossing, Voyager 2's PLS detected an abrupt disappearance of the outward-flowing solar wind plasma. Inside the heliosheath, the instrument had been measuring a decelerated but still flowing solar wind with a speed of roughly 100 to 150 kilometers per second and a density of approximately 0.001 particles per cubic centimeter. At the boundary, this flow ceased. The solar wind dropped to zero. In its place, the instrument detected a plasma population that was denser, hotter in terms of particle kinetic energy, and essentially stationary relative to the spacecraft. This was the interstellar plasma, material of galactic origin that had never been measured in situ by any instrument from Earth. The density measured by Voyager 2's PLS in the interstellar medium was approximately 0.05 to 0.06 electrons per cubic centimeter. This represented an increase of roughly 20 to 40 times over the solar wind density in the outer heliosheath. Context is essential here. By any terrestrial standard, this is still an extraordinarily thin medium. Earth's atmosphere at sea level contains approximately 25 quintillion particles per cubic centimeter. Even the best laboratory vacuum chambers contain trillions of particles per cubic centimeter. The interstellar medium at 0.05 particles per cubic centimeter is, by human experience, indistinguishable from perfect emptiness. But it is not emptiness. And the difference between the heliosheath's 1,000th of a particle per cubic centimeter and the interstellar medium's 500ths of a particle per cubic centimeter is physically significant. Denser plasma transmits electromagnetic disturbances differently. It supports different wave modes. It interacts more strongly with magnetic fields. It exerts more pressure. The fact that Voyager moved from a thinner medium into a denser one upon crossing the heliopause confirmed a key theoretical prediction. The interstellar medium exerts inward pressure that confines the heliosphere. The density jump at the boundary is the physical manifestation of that confinement. The temperature measurement added another piece to the portrait. Voyager 2's PLS measured the interstellar plasma temperature at approximately 30,000 to 50,000 Kelvin. This requires careful interpretation. Temperature, in plasma physics, refers to the average kinetic energy of particles. A plasma at 50,000 Kelvin contains particles moving at speeds of roughly 20 to 30 kilometers per second. This is fast by everyday standards, but slow compared to the cosmic ray particles sharing the same space, which travel at significant fractions of the speed of light. The critical nuance is that despite the high temperature, the thermal energy density of the interstellar plasma is vanishingly small because so few particles are present. You could immerse your hand in plasma at 50,000 Kelvin in the interstellar medium and feel absolutely nothing, because so few particles would actually strike your skin per second that the total energy transfer would be negligible. Temperature without density produces no perceptible heat. But the temperature is physically meaningful because it reflects the energy state of the medium. Plasma at 50,000 Kelvin has been heated by something. That something includes ancient shock waves from supernovae, turbulent dissipation of magnetic energy, and the general thermodynamic history of the local interstellar medium over millions of years. The PLS also measured a lack of significant bulk flow velocity in the interstellar plasma at the crossing point. Inside the heliosphere, everything moves outward because the solar wind imposes a radial flow. Outside, the plasma appeared nearly stationary in Voyager 2's reference frame. This was consistent with the spacecraft having entered a medium that is not being blown outward by any local star, but instead sits in a relatively quiescent state, slowly drifting through the galaxy as part of the local interstellar cloud that our solar system is currently traversing. The comparison between the two crossings revealed details that neither spacecraft could have provided alone. The two crossings sampled different parts of the heliosphere's surface. Voyager 1 passed through the upstream nose region heading northward at 122 astronomical units. Voyager 2 exited through the southern flank at 119 astronomical units, cutting through a section of the boundary angled differently to the incoming interstellar flow. The 3 astronomical unit gap between their crossing distances was the first direct evidence from 2 independent measurements that the heliopause varies in distance depending on where you cross it. But the differences went beyond geometry. The plasma conditions at the 2 crossing points were not identical. Voyager 2's direct plasma measurements showed a slightly different density and temperature profile at its crossing compared to what Voyager 1's indirect plasma wave measurements had indicated 6 years earlier at a different location. The magnetic field properties differed as well. Voyager 2 recorded a somewhat sharper magnetic transition than Voyager 1 had encountered, suggesting that the boundary's character varies along its surface. Some sections of the heliopause may be thinner and more abrupt, others may be thicker and more gradual, with more extensive mixing between solar and interstellar material. These differences are not surprising in retrospect. The heliopause is not a rigid structure. It is a dynamic boundary between 2 fluid systems, shaped by turbulence on both sides, buffeted by coronal mass ejections from within, and interstellar pressure variations from without. Expecting it to be uniform would be like expecting the surface of the ocean to be perfectly flat. The 2 Voyager crossings sampled 2 different patches of this surface and found 2 subtly different sets of conditions. Together, they proved that the heliopause is a complex, variable 3-dimensional structure rather than the simple spherical shell that textbook diagrams imply. The 2 crossings also allowed scientists to study how the heliosphere responds to solar activity changes over time. Between Voyager 1's crossing in 2012 and Voyager 2's crossing in 2018, the Sun had gone through the peak of solar cycle 24 and was descending toward the subsequent solar minimum. The heliosphere's properties had evolved accordingly. Comparing the 2 datasets showed how the boundary adjusts to changing solar wind conditions on timescales of years, providing a dynamic portrait that a single crossing could never have captured. Beyond the direct plasma measurements, Voyager 1's plasma wave science instrument provided a continuous record of the ambient plasma conditions through a different method. This instrument detects electromagnetic oscillations in the surrounding plasma, vibrations at frequencies determined by the local electron density. In the interstellar medium, the instrument recorded a persistent, low-frequency plasma oscillation at roughly 2 to 3 kHz. This faint signal represented the natural oscillation frequency of the interstellar plasma at its measured density, a kind of electromagnetic background tone produced by the medium itself. When NASA released an audio rendering of this signal in 2013, converting the plasma wave frequencies into the range of human hearing, the result was haunting. A thin, steady tone, almost like a sustained note on a glass harmonica, rising and falling slightly as the plasma density fluctuated. It sounded like nothing recorded on Earth or anywhere else in the solar system. It was the voice of the interstellar medium, the sound of the galaxy's own material vibrating at a frequency dictated by its physical properties. The scientific community reacted with appropriate caution, emphasizing that the audio rendering was a translation, not a literal recording of sound waves. The interstellar medium is far too thin to support acoustic vibrations in the conventional sense. What Voyager detected were oscillations in the electric field of the plasma, electromagnetic phenomena rather than mechanical pressure waves. The conversion to audio was a tool for human comprehension, not a claim that interstellar space is audible, but the underlying physics was genuine. The plasma hum is real. The interstellar medium vibrates at a characteristic frequency determined by its electron density, and Voyager's instrument detected that vibration directly. The hum proved scientifically valuable beyond its symbolic power. It provided continuous density tracking even during the long, quiet periods between solar-driven disturbances. Coronal mass ejections from the Sun occasionally send shockwaves rippling outward through the heliosphere and into the near interstellar medium. When these shockwaves reach Voyager's location, they cause the local plasma to oscillate more intensely, producing clear spikes in the plasma wave data that allow precise density calculations. These events are dramatic but infrequent. Between them, the quiet hum provides a baseline, a continuous background measurement that reveals the ambient state of the medium without requiring any external stimulus. The hum confirmed that the interstellar plasma density remains relatively stable over the timescales Voyager has been monitoring, hovering near 0.05 to 0.1 electrons per cubic centimeter. But within that stability, the data showed modest fluctuations, gentle rises and falls in the hum's frequency that correspond to small-scale density structures in the local medium. These variations suggest that the interstellar medium in our neighborhood is not perfectly homogeneous. Density ripples exist on scales of astronomical units, driven by the same turbulent processes detected by the magnetometer. The medium breathes, subtly and slowly, in a rhythm set by forces that have nothing to do with our sun. The persistent nature of the hum also carried a philosophical resonance that the science team did not overlook. For decades, popular imagination depicted interstellar space as silent. The void between stars was conceived as the ultimate quiet, a realm of absolute stillness where no vibration could exist because there was nothing to vibrate. Voyager proved this wrong. The interstellar medium is not silent, it hums, not loudly, not dramatically, but continuously, at a frequency that encodes its own physical identity. The space between stars has a voice, thin and faint but measurable, and Voyager was the first human instrument to hear it. Taken as a whole, the measurements from both spacecraft produce a coherent, detailed, and unprecedented portrait of the local interstellar medium. The particle environment is dominated by galactic cosmic rays arriving from all directions with a flux 2 to 3 times the highest levels ever recorded inside the heliosphere. Lower energy cosmic rays, the component most effectively excluded by heliospheric shielding, are present in abundances 5 to 10 times greater than inside the bubble. The anomalous cosmic ray population, a product of the heliosphere's internal physics, is absent. The particle census has shifted entirely from solar to galactic. The magnetic field is galactic in origin, oriented differently from the solar field, slightly stronger than the exhausted field in the outer heliosheath, and permeated by turbulent fluctuations on multiple timescales. The boundary between solar and galactic magnetic domains is not a knife edge, but a finite transition layer, where the two field systems blend over a distance of a fraction of an astronomical unit. That transition layer varies in thickness and character depending on where along the heliopause you cross it, as the two Voyager crossings independently demonstrated. The plasma is denser than the material in the outer heliosphere by a factor of 20 to 40, warmer in terms of particle kinetic energy, and essentially stationary relative to the spacecraft. It hums at a characteristic frequency determined by its electron density, a frequency that serves as a continuous monitor of ambient conditions. Small-scale density fluctuations within the plasma reveal a gently turbulent medium shaped by forces that have nothing to do with our sun. None of these conditions were fully anticipated before Voyager arrived to measure them. Models of the interstellar medium, built from decades of remote astronomical observation, had captured the broad strokes. Scientists knew the interstellar medium was thin, magnetized, and permeated by cosmic rays, but the specific values differed from many pre-crossing predictions in ways that mattered. The plasma density at the heliopause was slightly higher than several widely cited models had estimated, suggesting the local interstellar medium exerts more pressure against the heliosphere than previously calculated. The magnetic field transition was more gradual than the clean directional flip that most simulations produced, revealing a boundary layer more complex than theory had anticipated. The cosmic ray flux distribution in the lowest energy ranges, where the heliosphere's shielding is most effective, showed a steeper increase than some models predicted, meaning the heliosphere blocks even more low-energy radiation than scientists had given it credit for. And the turbulence spectrum, both magnetic and density, proved richer than many models assumed, indicating that the interstellar medium near the Sun is more dynamically active than the quiet, equilibrium state that simplified theoretical treatments often invoke. Each of these discrepancies between prediction and measurement was individually modest. None represented a dramatic failure of theory, but collectively, they demonstrated something that scientists already knew in principle but could now confirm in practice. Remote observation can constrain the possibilities. Only direct sampling can select the truth. Models of the interstellar medium, however sophisticated, are built on assumptions about conditions at a location that had never been visited. Voyager visited, and the truth, as measured truth often does, proved more complicated and more interesting than the models had suggested. The truth is not the peaceful, inert, empty void that casual language suggests when people say, the space between stars. The interstellar medium is an active environment. It is irradiated continuously by galactic cosmic rays, carrying energies that range from millions to billions of electron volts per particle. It is threaded by a magnetic field shaped by galactic scale processes operating over timescales of millions of years. It is mildly turbulent, with density and magnetic fluctuations that reflect the ongoing dynamical evolution of the gas and dust between stars. It is cold in the sense that any macroscopic object placed within it would radiate away its heat and equilibrate to temperatures just a few degrees above absolute zero. It hums at a frequency only a plasma wave detector can perceive, and it extends, with broadly similar properties, for light years in every direction. There is a tendency, when discussing the interstellar medium, to emphasize its emptiness, and it is empty by any standard that a human body would recognize. The density is so low that a cubic volume the size of Earth would contain only a few thousand tons of material, roughly the mass of a single large ship. The particles are so sparse that individual atoms may be separated by distances measured in centimeters or meters. The medium is transparent to light. You could see through it for light years without the faintest hint of haze. But this emptiness is deceptive. The medium is not inert. It is electromagnetically active. It is dynamically structured. It is bathed in a radiation field that originates from the most violent events in the galaxy. It carries the debris and energy signatures of supernovae that exploded before our solar system existed. And it presses inward against the heliosphere from every direction, continuously testing the boundary, waiting for the solar wind to weaken. Voyager 1 and Voyager 2 did not find emptiness. They found a medium. A thin one, yes. A nearly invisible one. But a medium with definable properties, measurable characteristics, and physical consequences for anything immersed within it. The instruments aboard those two aging spacecraft provided humanity with its first direct taste of the environment that fills the overwhelming majority of our galaxy. These measurements are not merely academic. Every number in the data set, every particle count and field strength and density estimate, carries implications for the most ambitious question humans have ever asked: whether it is possible to travel between the stars. The answer to that question depends not only on how far the stars are, but on what lies between them. Voyager has now told us, in hard data, what that something is, and the implications are more sobering than the distance alone would suggest. The cosmic ray flux is unshielded and continuous. The magnetic environment is alien and turbulent. The plasma is thin but dynamically active, humming with a voice that encodes the physical state of the galaxy itself. The temperature for any passive object approaches absolute zero. The space between the heliosphere and whatever distant astrosphere might exist around the next star is not a corridor, it is an ocean. And Voyager has now measured the depth, the salinity, and the current of that ocean for the first time. But the data does not end with description. Every particle count and field measurement and density figure points toward a set of conclusions that are difficult to hear and impossible to dismiss. They concern the future of exploration, the isolation of every star system in the galaxy, and the true nature of the Milky Way as a place where the space between stars is not merely vast but actively, measurably punishing to anything that enters it. The data is in. The particle counts are recorded. The magnetic field vectors are stored in NASA's archives. The plasma densities are published in peer-reviewed journals. Voyager 1 and Voyager 2 have given humanity its first direct measurements of the interstellar medium, and those measurements now sit on hard drives in Pasadena, California, available to anyone with the curiosity to examine them. The question is no longer what exists beyond the heliosphere. The question is what it means that the answer turned out to be this harsh. Begin with the most practical implication. Any object that leaves the heliosphere must survive the interstellar medium on its own terms. There is no partial credit. There is no gradual adjustment. The solar wind drops to zero, the heliospheric magnetic shielding vanishes, the galactic cosmic ray bombardment begins immediately and does not relent. Not for a day, not for a year, not for the centuries or millennia that any conceivable interstellar transit would require. Consider what this means for spacecraft engineering. Every vehicle humanity has ever sent into space carries a hidden assumption baked into every specification and every design margin. The radiation models presuppose the heliosphere's shielding. The thermal budgets assume proximity to a star. The power systems rely on solar energy or radioactive fuel that will be exhausted long before any interstellar crossing is complete. Remove all of these assumptions simultaneously, and you are left with a design problem that no existing spacecraft architecture can solve. Radiation shielding is the most immediate challenge. Galactic cosmic rays, as Voyager's instruments confirmed, arrive from every direction with energies spanning from millions to billions of electron volts per nucleon. The most common cosmic ray particles are protons, but the flux includes helium nuclei, carbon, oxygen, silicon, iron, and other heavy ions, all traveling at substantial fractions of the speed of light. When these particles strike a spacecraft hull, they do not simply bounce off or get absorbed cleanly. They interact with the nuclei of the shielding material, producing cascades of secondary particles. Neutrons, protons, pions, muons, and gamma rays spray inward from the impact site, sometimes depositing more total energy inside the spacecraft than the original cosmic ray would have delivered on its own. This secondary particle production is one of the cruelest facts of radiation physics. For galactic cosmic rays above certain energies, adding more aluminum shielding actually increases the dose to anything inside rather than decreasing it. The shield becomes a particle multiplier. Researchers at NASA and other agencies have studied alternative shielding materials for decades. Hydrogen-rich compounds perform better than metals because hydrogen nuclei are close in mass to incoming protons, allowing more efficient energy transfer that degrades the cosmic ray's energy without producing heavy secondary fragments. Polyethylene, water, and even liquid hydrogen have been proposed as shielding materials. The best estimates suggest that optimized hydrogen-rich shielding can reduce the galactic cosmic ray dose by roughly 30 to 50%. This is meaningful, but insufficient for a journey lasting decades. A crew exposed to even half the unshielded interstellar cosmic ray intensity for 20 or 30 years would accumulate radiation doses far exceeding the career limits established by every major space agency. The cancer risk alone would be substantial. The potential for central nervous system degradation, cardiovascular damage, and cataract formation adds further layers of concern. Active shielding concepts, using powerful superconducting magnets to generate an artificial magnetosphere around a spacecraft, have been proposed as alternatives. The idea mimics what the heliosphere does naturally, using magnetic fields to deflect incoming charged particles before they reach the hull. The physics is sound. The engineering is nightmarish. Generating a magnetic field strong enough to deflect galactic cosmic rays with energies of billions of electron volts would require superconducting coils of enormous size, carrying currents that would produce intense magnetic fields in the crew's living quarters with their own biological effects. The mass and power requirements of such a system, using any technology that currently exists or is plausibly foreseeable, would dominate the spacecraft's total mass budget, and the field would need to be sustained continuously for the entire journey, without interruption, without failure, without degradation, for decades. Energy is the next insurmountable problem. Inside the heliosphere, spacecraft can use solar panels out to roughly 5 astronomical units, beyond which the solar flux becomes too weak for practical power generation. Radioisotope thermoelectric generators extend the range much farther, as the Voyagers have demonstrated, but their power output decays steadily as the radioactive fuel decays. Plutonium-238, the isotope used in Voyager's generators, has a half-life of approximately 87.7 years. After one half-life, the power output drops by half. After 2 half-lives, it drops to a quarter. A journey to the nearest star at Voyager's current speed would last over 70,000 years. Roughly 800 half-lives of plutonium-238. The fuel would be completely exhausted within a few centuries, leaving the spacecraft without power for the overwhelming majority of the transit. Nuclear fission reactors offer higher power output and could potentially last for decades, but even fission fuel is finite. Uranium or thorium reactors would need to be designed for operational lifetimes far exceeding anything ever built on Earth, where the longest operating reactors have functioned for roughly 60 years with extensive maintenance. A reactor on an interstellar spacecraft would need to operate autonomously, without maintenance, without refueling, and without spare parts for a duration that would strain any engineering margin. The interstellar medium itself offers no alternative energy source. There is no sunlight to collect. The particle density is far too low to fuel any conceivable ram scoop or drag-based system at the speeds a spacecraft would be traveling. The magnetic field energy density is negligible. The thermal energy of the plasma, spread across such extraordinary volumes at such low density, is thermodynamically inaccessible. An interstellar spacecraft would carry every joule of energy it will ever use, from departure to arrival, with no possibility of resupply. Temperature compounds the problem. Far from any star, an unheated object in interstellar space radiates its thermal energy into the cosmic microwave background and equilibrates at a temperature of roughly 2.7 Kelvin, approximately minus 270 degrees Celsius. At this temperature, most lubricants solidify, battery electrolytes freeze, structural metals become brittle, electronic components designed for the temperature ranges encountered inside the heliosphere cease functioning. Maintaining a habitable temperature inside a spacecraft requires continuous heating, which requires continuous power, which brings the energy problem back to the foreground. Every watt spent fighting the cold is a watt unavailable for propulsion, communication, life support, or radiation shielding systems. And then there is the distance itself, made meaningful not merely by its magnitude but by the nature of the medium that fills it. The nearest star system, Alpha Centauri, lies approximately 4.3 light-years from the Sun. At Voyager, one's current velocity of roughly 17 kilometers per second, reaching Alpha Centauri would require more than 73,000 years. Even at 10% of the speed of light, a velocity far beyond any propulsion technology that currently exists or is under serious engineering development for macroscopic spacecraft, the transit would last approximately 43 years. During every one of those years, the vehicle would be immersed in the environment Voyager measured. Full cosmic ray flux, no solar power, temperatures near absolute zero, no shelter, no harbour, no possibility of rescue or resupply. 10% of light speed is itself an extraordinary velocity. It corresponds to roughly 30,000 kilometers per second, nearly 2,000 times faster than Voyager 1. Achieving this speed with a spacecraft massive enough to carry meaningful payload, let alone a human crew, would require energy inputs that dwarf any propulsion system ever built. Chemical rockets are entirely inadequate. Ion drives, solar sails, and nuclear thermal propulsion all fall short by orders of magnitude. Only concepts like nuclear pulse propulsion, antimatter engines, or laser-driven light sails even approach the theoretical capability, and none of these have progressed beyond preliminary design studies. The engineering challenges of building, testing, and operating any of these systems reliably enough for a decades-long interstellar journey remain immense. But set aside the propulsion problem entirely. Assume that some future civilization solves it. Assume they can accelerate a spacecraft to 10% of light speed and sustain that velocity for decades. They still face the interstellar medium. They still face the cosmic ray bombardment. They still face the energy deficit and the thermal hostility. The distance is not the only barrier. The medium is. This realization extends far beyond human engineering. It applies to every star system in the galaxy. The Milky Way contains somewhere between 200 billion and 400 billion stars. Each star that produces a stellar wind, which includes most stars on the main sequence, inflates its own protective bubble analogous to our heliosphere. These astrospheres vary enormously in size and effectiveness. Massive hot stars with powerful winds create large astrospheres that may extend hundreds of astronomical units. Small red dwarfs with feeble winds produce astrospheres that may barely encompass their habitable zones. Some stars in particularly dense regions of the interstellar medium may have astrospheres compressed to a fraction of the size our heliosphere enjoys in its relatively low-density galactic neighborhood. But regardless of the size of any individual astrosphere, the space between those bubbles is filled with the interstellar medium, and Voyager has told us what that medium contains: galactic cosmic rays, magnetic turbulence, cold plasma, emptiness punctuated by radiation. Every star system in the galaxy is an island surrounded by this ocean. The astrospheres are harbors. The interstellar medium is the open water, and the open water is hostile. The volume of the galaxy occupied by astrospheres is vanishingly small compared to the total volume. If you could somehow inventory the entire Milky Way, adding up every stellar wind bubble around every star, the combined volume of all those protected regions would represent a tiny fraction of the galaxy's total volume. The overwhelming majority of the Milky Way, measured by volume, consists of the interstellar medium. The thin gas, the magnetic fields, the cosmic rays, the cold, the emptiness, that is what the galaxy is made of. Stars and their protective bubbles are rare exceptions, oases scattered across a desert that stretches 100,000 light-years from edge to edge. This perspective inverts the common image of the Milky Way. When people picture our galaxy, they imagine a luminous spiral of stars, dense and glittering, a cosmic city full of potential destinations. The reality is closer to a vast, dark, irradiated wilderness with tiny campfires scattered impossibly far apart. The campfires are real. The stars are there, but the wilderness between them is the dominant feature, and Voyager has measured its hostility firsthand. Every civilization that might exist in the galaxy, if any others do exist, faces the same barrier. They sit inside their own stellar bubble, shielded from the galactic environment by their own star's wind. If they look outward and dream of reaching the next star, they confront the same interstellar medium that Voyager measured, the same cosmic ray flux, the same absence of energy sources, the same thermal hostility, the same radiation-saturated void stretching light years in every direction. The physics does not change depending on who you are or what star you orbit. The interstellar medium is the same ocean for every island. This has implications for one of the most famous questions in science. If the galaxy contains billions of potentially habitable planets, and if even a small fraction of those develop technological civilizations, where is everyone? The Fermi paradox, the tension between the apparent probability of extraterrestrial intelligence and the absence of any evidence for it, has generated dozens of proposed solutions over the decades. Some invoke the rarity of intelligence itself. Some propose self-destruction as a universal fate for technological species. Some suggest that civilizations exist but choose not to communicate. Voyager's data offers a different, more physically grounded contribution to this conversation. The interstellar medium is not a highway connecting civilizations. It is a barrier separating them. Every star system is enclosed within its protective bubble, surrounded by a medium that punishes anything that ventures into it. Crossing that medium is not merely a matter of sufficient speed or fuel. It is a matter of surviving an environment that continuously degrades, irradiates, and drains any object that enters it. The silence of the galaxy may not reflect the absence of other civilizations. It may reflect the reality that the space between civilizations is a far more formidable obstacle than distance alone suggests. Light and radio waves cross the interstellar medium with relative ease. Electromagnetic signals propagate freely through the thin plasma, attenuated by distance and slightly dispersed by the free electrons in the medium, but fundamentally capable of bridging the gaps between stars. Communication across interstellar distances is physically possible, even if the round-trip signal delay to the nearest star exceeds 8 years. But sending a physical object, a probe, or a ship requires surviving the medium rather than merely passing a signal through it. That is a categorically different challenge. The distinction between sending a signal and sending an object illuminates something important about our galaxy. The Milky Way may be a place where information can travel between star systems, but where matter effectively cannot. Civilizations might detect each other's signals across hundreds or thousands of light years, while remaining permanently unable to visit each other in person. The galaxy could be full of voices and empty of visitors, full of knowledge and devoid of contact. Every civilization an island, able to see the distant campfires of others, but unable to reach them through the hostile ocean that separates every star from its neighbors. This is the terrifying truth that Voyager's measurements illuminate. Not that the spacecraft traveled far, although it did. Not that it survived for decades, although it has. The terrifying truth is the nature of what it found. The space beyond the heliosphere is not the passive emptiness of popular imagination. It is not a benign void waiting to be traversed. It is a medium that degrades what enters it, not through drama or spectacle, but through the relentless accumulation of particle impacts, thermal drain, and the complete absence of any resource that a complex system requires to sustain itself. And it fills the overwhelming majority of the galaxy. We live inside a bubble. That bubble is inflated by an average star, maintained by a continuous outpouring of charged particles, and sustained by a nuclear fusion process that has been running for 4.5 billion years and will continue for roughly 5 billion more. Inside this bubble, the radiation is manageable. The temperatures, while extreme by human standards, are moderated by solar heating. The magnetic environment is organized by the sun's field. The conditions permit the existence of complex chemistry, liquid water, atmospheric retention, and biological evolution. Outside this bubble, none of those conditions hold. The radiation is galactic in origin and unshielded. The temperature for any passive surface approaches absolute zero. The magnetic field is alien in structure and turbulent in character. The medium offers no energy, no resources, and no shelter. Everything that makes the interior of our solar system hospitable traces back to the heliosphere's ability to hold the galaxy at bay. Voyager 1 and Voyager 2 will go silent within the next several years. Their plutonium will no longer generate enough electricity to power their transmitters. The last data will arrive at the Deep Space Network, be decoded, archived, and studied, and then silence. The spacecraft will continue outward, carried by their own momentum through the interstellar medium, cooling to the ambient temperature of the cosmic microwave background, drifting through the galaxy as inert artifacts of a species that once lived on a small rocky world 26,000 light-years from the galactic center. Voyager 1 will pass through the vicinity of Gliese 445 in approximately 40,000 years. It will not stop. It cannot stop. It will drift through that star's neighborhood, perhaps passing through the outer reaches of an alien astrosphere, and continue onward. It carries a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, greetings in 55 languages, music from Bach to Chuck Berry, the sound of wind and rain and a human heartbeat, diagrams showing Earth's position relative to 14 pulsars, a cosmic address designed to remain valid for hundreds of millions of years. The record was mounted on the spacecraft's exterior. It is exposed to the full interstellar cosmic ray flux. Over tens of thousands of years, that radiation will gradually degrade the record's surface. The grooves that encode the audio will be slowly eroded by particle impacts. The images etched into the disk will blur. The gold plating will endure longer than most materials, but even gold is not immune to the steady rain of high-energy particles that Voyager's own instruments measured and reported. The message, encoded with such care and hope in 1977, will eventually become unreadable. The interstellar medium, hostile and indifferent, will erase it. But before that erasure, the data reached us. And the data describes something that should change how every person on Earth understands their place in the cosmos. We are not residents of a galaxy brimming with accessible destinations. We are inhabitants of a single protected enclave within a galaxy that is overwhelmingly composed of the hostile medium between stars. The stars themselves are distant beyond meaningful human experience. The medium between them is harsh beyond casual intuition, and the bubble that protects us is finite, maintained by a star that will not burn forever, wrapped around a solar system that occupies an infinitesimally small fraction of the Milky Way's total volume. The Voyagers did not discover aliens. They did not find wormholes or shortcuts. They did not encounter anything supernatural or inexplicable. What they found was far more unsettling than any of those fictions. They found reality, the real, measured, physically confirmed conditions that prevail in the space beyond the sun's protection. Cold, irradiated, magnetically turbulent, empty of resources, devoid of shelter, stretching for light years in every direction before the faintest warmth of another star's influence could be detected. There is something in the human spirit that looks at the night sky and sees possibility, destinations, worlds to explore, neighbors to find. This impulse is beautiful, and it is the same impulse that built the Voyager spacecraft, launched them on their impossible journey, and kept them alive for decades beyond their design life. That impulse deserves respect. It may even deserve pursuit, but it must be pursued with honesty about what lies between here and there. The galaxy is not a map with roads connecting the dots. It is an archipelago of isolated islands in an ocean of radiation and emptiness, and the ocean is wider, colder, and more punishing than most people have ever been told. Voyager went into that ocean. It tasted the water, it measured the currents, and it sent back the truth. The truth is that what lies beyond our solar system is not merely far, it is fundamentally hostile. The heliosphere is not just a boundary, it is a refuge. The sun is not just a star, it is a shield. And the terrifying truth about what Voyager found is not that it travelled farther than any human object has ever gone. It is that everything it measured on the other side confirms what the numbers always suggested, but no instrument had ever verified. The galaxy, for all its grandeur and all its billions of stars, is made mostly of the space between those stars. And that space is no place for anything that depends on warmth, shelter, or the protection of a star to survive. Voyager told us what the galaxy really is, not from a distance, not through inference, through contact, through the direct touch of instruments against the medium that fills the Milky Way. And what the galaxy really is, for anything born inside a heliosphere, is a warning written in cosmic rays and magnetic fields and cold, thin plasma humming at 3 kilohertz in the dark. We received the warning. Whether we heed it, or whether we find a way to answer it, is a question the Voyagers cannot help us with. Their work is nearly done. The data has been delivered. The rest belongs to the species that built them, a species that lives on one world, orbiting one star, inside one bubble, in a galaxy that stretches 100,000 light years in every direction and is filled, almost entirely,